So when solving systems of linear equations, a system of linear equations looks like this. We have two linear equations and two variables. We have x and y as variables, a, b, c, d, e, f are numbers that we know. And we already know how to graph these individually. That's graphing straight lines, and there's a number of ways we can do it. And in this section, we're going to talk about solving by graphing. And so here's what we're looking for. There's three different cases of what happens. So more often than not, when you're working on these, there's going to be a solution. And after you graph the two lines, you're going to see something that looks like this, and something that looks like that, and they're going to intersect at a point. So when you draw two lines in a plane, more often than not, they're probably going to meet at some point. The second case is you have two lines that are going off in the same direction. They're both parallel. So parallel lines never meet. Let me address that would be a solution, and we have a point A, B in that previous one. If they're parallel, there is no solution because they're never going to meet. And finally, the third case, which is a little weirder than the others, is you have two lines that are basically on top of one another. And this is infinite solutions. If there's infinite solutions, they're basically the same line. And we'll talk about it, we'll address it more when we see an example. But WebAssign is going to want you to type something along those lines in for your answer. And we'll see a concrete example. Where you get points x and mx plus b, and don't forget that mx plus b is a y value because y equals mx plus b. And we'll actually see some concrete examples with that. So that's what we're looking for in general. So I have three examples I want to get through. And example one. So we're going to solve the system by graphing. 2x plus y is 4, x plus y is 2. And sometimes you're going to see a brace next to the system, and that says these two are attached, and sometimes you won't. And it really depends on who's writing it and probably their mood. If you're just looking at a system of equations and you see the brace, you know it's a system of equations. If you don't see a brace, you may or may not know that they're a system. It depends on context. I'm probably not going to write that most of the time. So when it comes to graphing these, you can do however you want. So I'm gonna graph these by plotting intercepts. Let's get a graph going. X and Y. And for the first equation, my x-intercept would be, so I can plug in y, I get 2x is 4, so I get x is 2. So I get 2, 0. And if you need to pause it to find that yourself, go ahead. My y-intercept, I plug in 0 for x, I'm going to get 4 for y, and that's what's 0, 4. Don't forget, intercepts are points. They're ordered paired with parentheses and a comma. And so before I move on, I'm actually going to go ahead and plot those. We need to work with one equation at a time. If you find a whole bunch of intercepts or a whole bunch of points, start plotting them before you connect the dots. It's easy to get confused on what's going where. So I found the points for the yellow line, or the line highlighted in yellow. So let me plot those points. And I'm going to connect the dots. We're going to go edge to edge on the graph. because we don't know where they're going to meet. So if I use intercepts on the other one, so let's talk about the blue line. Actually, I can highlight that in yellow, just to make sure we know that that's where that's from. If I'm looking at the blue line, and if I plug in 0 for y, I get x is 2, so 2, 0. Hey, I think we found our solution. And similarly, 0, 2. And so I can plot my points, and I can connect my dots, and we're going to get two lines that have slightly different slopes, and they intersect at the x-intercept. Let me highlight things in blue. And our intersection is the solution, and the solution is at 2, 0. And that is how you solve systems of equations by graphing. I chose to use intercepts because these were in standard form and the intercepts were relatively friendly. If you want to just plot points, that's fine. If there's no instructions on how to graph these, you pick your favorite method. And that might depend on the situation that you're in. My second system, I'm going to solve 2x plus y is 4 and y equals negative 2x minus 2. And that first one matches the equation above. So I know this one, the yellow, I know I have 2, 0 and 0, 4 for my intercept. So I'm not going to bother generating new points for that. This we don't know what it looks like yet. So let's generate some points. I got x, y, so I'm going to plug in my x values. Let's see, I'm going to plug in negative 2, 0, and let's plug in 1, just for the hell of it. All right, so if I plug in negative 2, I get negative 2 times negative 2, that's 4. 4 minus 2 is 2. If I plug in 0, I get negative 2, because that's a y-intercept. And if I plug in 1, I get negative 2 minus 2, and that would be a negative 4. Okay, so I have my intercepts in yellow. I'm going to have points from the blue line. So let's get a graph going. So plotting the yellow points first. 2, 0, and 0, 4. I'm going to draw that line. Again, work with one line at a time. In hindsight, I probably should graph that first. But it's okay. We'll get it done. So let's plot the blue one, negative 2, 2, 0, negative 2, and 1, negative 4. And drawing a straight line is important here because we have something happening that's not straight. So, well, still not straight, but I think we get the point here. What's going on with these two lines? Had I drawn them with a straight edge, which again is hard on the tablet, I would have had parallel lines. So these look like they're going in the same direction. And since these are parallel, they're never going to meet. So there can be no solution on this example. And third, let's look at the example that I said would be the weirdest. And we're going to look at 3x plus y is 0, and 2y equals negative 6x. So I can make an observation here. if I solve this equation for y, I'm going to get y equals negative 3x. And if I solve this equation for y by dividing everything by 2, I'm going to get y is equal to negative 3x. So if we recognize we're in a situation that we have the same line, then we already know what the answer is, but we're already asked to solve by graphing. And that reminds me, I'm going to scroll up and look at that last example because there's something that's going on, which will tell us as parallel. But let's get this one done first. So both these equations are going to be y equals negative 3x. And let's plug in negative 1, 0, and 2. So if I plug in negative 1, I'm going to get y is equal to 3. If I plug in 0, I get 0. If I plug in 2, I'm going to get negative 6. So I went through that pretty quickly, but if you need to pause it to double check my math, go for it. Let's get the points plotted. So negative 1, 3, 0, 0, and 2, negative 6. And those look like they're laying on a straight line, which is good. And so we're going to connect the dots, and that is one line. So on a test, I would accept infinite solutions if you wrote that. But in WebAssign, it's going to want you to write x and negative 3x. So don't forget that y is mx plus b is the point slope form of a line where y depends on x. And if WebAssign wants you to enter your answer as a point, you're going to put in x because x can be anything because this is a line and a line has an infinite number of points. And so we're going to call the x value x. And the y value is going to be whatever the mx plus b that gets spit out. And if you notice, that's in point slope form. I'm sorry, slope intercept form, where the intercept is 0, 0. And so this 3x or negative 3x is my y value. And that's how WebAssign is going to want me to enter your points. Okay. So I have a few things to talk about for that second example. If you were to solve that first equation for y, you would get y is negative 2x plus 4. And when you compare it to the second equation, which is y is negative 2x minus 2, these things have the same slope, but they have different y-intercepts. If they have the same slope, they're going in the same direction. They have different y-intercepts. They're different lines. Since they're going in the same direction, that would be parallel. And so that's one way you can check if you have parallel lines. If you get them in slope-intercept form, you have the same slopes but different intercepts. Now, there's some language that you're going to see popping up from time to time in literature. We don't see it too much outside of pre-calculus, but if a system has a solution, we call that consistent. Right, so there's a solution, so we call that consistent. If they're parallel, we say that's inconsistent. And if we have the same line, that's going to be consistent but dependent. So we have consistent dependent. And so you might see that in the literature. I never test on that in my classes, but sometimes it pops up in homework problems. Or if you're watching videos made by someone else, they might use that terminology. So I figure I'd let everyone know. We have 2 more videos to go. One's on solving systems by substitution method, and the other one's the elimination method.